Okay, class. So let's see about that midterm. Got the scores back from Madura. You guys have hopefully seen them by now. I felt that the average was kind of low. It was 40 points. So I showed the test to another professor in the math department here. She said she thought that it was, I guess, on the hard side for a 50-minute test. So I decided to make one of the problems on the test essentially like an extra credit problem, meaning it's graded out of 60 points instead of 70, which puts the average at a more reasonable percentage. Those are the types of problems, though, that you can expect on the final. Right? Like, so the final, you'll have 3 hours to do it. You'll have a lot more time. Like, being rushed shouldn't be a factor on the final. So, yeah, you can expect more like that. Now, besides essentially curving the scoring for the midterm, I did decide to offer some more extra credit points. Like, I was putting out those practice problems on WebAssign to practice for the midterm. So I'll include the points that you get from doing those problems as extra credit points, meaning they're as good as homework problems. To be honest, I don't really like all this talk about points because your motivation for learning this stuff shouldn't be like with your focus just on what grade you're going to get in the class. That said, I still realize grades are important, and in some cases, it's kind of like the only way you can really motivate some students. So thus, I have to talk about them. But really, like in a perfect world, you guys would just want to do it just so you could like figure it out and understand it. And that's what I'm hoping like some of you guys will do. They have classes, even in some undergraduate classes, they like Calculus 2 classes like this one in some schools with some professors where the homework is totally optional and it's all on the student to do as much as they see fit, as much as they think they need to in order to understand the material, and that then they'll have to be tested on it, like in class. But like no mandatory homework whatsoever, which puts all the responsibility on the student. Now, you guys probably remember, like back in high school, you had a lot less responsibility, and you had to do all this different homework. They would even check your attendance, which I don't do. College is kind of like we try and find a balance in the middle. We found we can't. If I just left all the responsibility on you to do as much studying as necessary, some of you would do fine, but we've also found that a lot of students just fall ridiculously behind, and it doesn't work. So that's one of the reasons that homework is mandatory and is part of your grade. So let's see. I've also wanted to do some other stuff with extra credit. Like I wanted to give you a chance to correct whatever mistakes you made on the midterm. Problem is, I've come up with so many different things, kind of extra things for this class, like all the different extra credit things and other ideas that I've been trying that I'm worried it's just like too much stuff, Like the syllabus was already long for this class, and I don't want things to get too complicated with too many things for both you to keep track of and for me to keep track of. Like when I do grading, I'm going to have to assemble scores from like 10 different sources to figure out what grade you guys get. I don't know if I'll be able to do something like that, but definitely, like super crucial, figure out what went wrong on the midterm and be able to correct it. And at the very least, I'm just going to put one of the problems from one of the midterms, just straight copy of that problem on the final. So you'll definitely want to make sure you could do any of the midterm problems before the final comes around. And another order of business first is, you guys probably know evals are being asked for by the school. So I would ask you guys to go on there and evaluate me. It's one of the ways that we get to know if we're doing a good job. as I've said before, this is my first time teaching at this level, so I've tried a lot of different things, and I would be interested in hearing like what worked and what didn't work. So if you have constructive criticism, I'd love to hear it. And if you think I did a good job, I'd also love to hear that, and that could potentially help me in what I hope to do, which is continue being a teacher or a professor or instructor. So yeah, go submit the evals, and let's see, anything else? Any questions before we get started? Yes?
About how many problems will be on the final?
Oh, I haven't even thought about that yet, but it's kind of like 2 midterms maybe, off the top of my head, something like that. Yeah, I don't know, but don't hold me to that. Any other questions? Maybe 3, I don't know, I haven't thought about it. Yes? Yeah. And a few people are asking with regards to extra credit, it is possible to get more than 100% on your homework grade. So yeah, in which case that will account for more than 20% of your grade in the class. So you can, that is a way you can help like boost your percentage in the class. Oh, and with regards to those hard like proof type problems that I made as extra credit, those were due today, so I'll post solutions to those later today, which those of you that attempted them, you guys can, I encourage you to check out the solutions and see if you did them right. Oh, and also I want to thank Maddie. I mean, she's not, I call her Maddie, Madura. She's not here, but for sending out that email, like admonishing you guys. It's probably admonishing the students that are in class watching the video cast right now, huh? Like, you guys are the good ones that are actually here. But it's the bums that stayed home and didn't come to class and just watched the video cast. They probably are the ones that are, like, not writing correct notation for integral signs and stuff. So, yeah, to all of you that are hearing this or watching this or here now, listen to what Maddie had to say. She had some good advice, and make sure you follow her recommendations and practice up on that stuff before the final. Okay, all that. So now I guess we can get to the math. So heading into the home stretch here in this class is one of the, I want to say coolest, although I think all this series stuff is cool, but also one of the most important topics in this class. This class culminates in Taylor series and power series, which is basically it's representing functions as polynomials, as infinite polynomials, and I'll show you what I mean. But this whole class, like up until this point, including 20A, has kind of been building up to this subject right here. It's one of the most important things in engineering. You'll use the things that we're going to show you in engineering over and over and over. Just the applications are so numerous. I still use these things all the time. So, okay, let me give a sort of motivating example as to what these last few classes are going to be about. So here's the idea. Let's say we want to look at the graph of the function here. How about sine x? So this is y equals sine of x. And you have already learned in 20A how to graph a tangent line to a curve. So let me draw a tangent to this curve. How about at the origin? Does anyone know what the slope of the tangent to the curve of sine x at the origin is? 1. So this is in fact the line y equals x. And it's the tangent to the curve of y equals sine x at the point 0. Okay, So the whole point of tangents to curves, if you remember, was they are good approximations to the curve. So near 0, if you plug in sine of a number and you plug in x, you get pretty close to the same value, right? Like you've probably already seen this demonstration. Go plug in like sine of 0.1 on your calculator, and it's pretty close to 0.1. So this is a good approximation to the graph of sine x near the origin. So what if we ask the question, well, can we do better than that? Can I get an even better approximation? Or how about an approximation that's better even farther away? Because look, clearly this does not approximate the graph like over here. It's totally different. The green line and the white line are way off from each other, you know, over here, but here they're good approximations. So I will tell you without proof that we can do a better approximation if we start including higher powers of x. So like, well, what would the next power be? Would be a quadratic function. And if we wanted to approximate it even better than that, we could use a cubic. So a cubic approximation would be, okay, let's see if I can do this. It's going to look like, and this, which I'm going to give you a formula for this line I just drew without proof for the moment. It's the graph of x minus x cubed over 3 factorial. All right, or x minus x cubed over 6. So that's the graph that I just drew. And it's, if you can kind of see, it's a better approximation to sine. You guys agree the red line is a better approximation? And what happens is as we allow higher and higher powers of x, we can get better and better approximations. So y equals x minus x cubed over 6 is a better approximation. And I say this without proof, but I will prove it eventually. We just have to build up some material first in order to get to that point. And it's going to take me a few lectures to do that. But so the idea here is representing functions as polynomials, arbitrary functions, like sine, for example, as polynomials. Now, recall what a polynomial is. So this is just the definition of a polynomial. And it's got some constant term, it's got a linear term, a squared term, and up to some finite order nth term, where n is the degree. So since we want to allow arbitrarily high powers of x, we're actually, what we're going to have to do is allow infinite degree polynomials, right? Like this only goes up to the nth power. But what if I just let it go up to the infinite power? So that the terms never stop. That's actually technically not called a polynomial anymore. By definition, the word polynomial means finite degree. So I'm going to just say, I'm going to insert the word infinite polynomials, and it's actually bad terminology. The correct term for an infinite polynomial is a power series. So I'll give you the precise definition of a power series. You could think of it, though, as an infinite polynomial. Like, while technically not correct, that's what it is. So it's any function where it's just a sum of powers of x. But the sum goes all the way up to infinity. Let's use about k. I don't like this being sloppy here. It's a sub k x to the k. Starting at 0 and going up to infinity. So it's an infinite series, but one of the terms, it's got an x in it, the variable x. So this is a function. But as we have seen, really crazy things can happen with infinite series. Like if they don't converge, you can get nonsense results from infinite series. So I wrote an equal sign right here. This might not even rigorously be true. Like I can't really say an equal sign here if the right side is not defined. So let's just suspend your disbelief for the moment. I'll put like the equal sign in quotations. And really I should say equal when it's defined. So and so now you'll see why we need all these tools that we just finished learning about in the last few sections about convergence. You had to learn all this convergence business in order to know if this even makes sense. So that's why all that stuff was really important. And by the way, so this is a power series. I actually I could shift this series over so that I could shift this over by, say, c units and write it like, and if I shifted it over, instead of x, I would put x minus c to the k. So we call this a power series centered at 0. But in general, we should center it at some arbitrary number c. So this is the general formula for a power series centered at c. Except usually c is 0, but not always. It doesn't have to be. It's most convenient when it is. The notation is easiest when it's centered at 0. Most of our examples, but not all of them, will be centered at 0. Okay, so we've actually already seen examples of power series, though maybe not quite in using that terminology. But here's one. So how about 1 plus x squared plus x cubed, and so on, which is the same as x to the k from k equals 0 to infinity. This is one we're familiar with. This is the, which one? the name of this series? It was just higher and higher powers? Yeah, it's a geometric series. So this is going to be a super important example in what follows. We're going to go back to it over and over again. And thankfully, we already have some results for geometric series, like for what they sum up to and so forth. So I'm going to use those right now. So recall that if the absolute value of x is less than 1, then I can actually get an explicit closed form formula for this series. And it's 1 over 1 minus x. How about if the absolute value of x is bigger than 1? I showed you guys this. Do you remember what happens if I try to add up powers of x if x is bigger than 1? Like what happened with 1 plus 2 plus 4 plus 8 plus so forth? Yeah, this diverges. So I did mention this, that if you tried to plug in a number bigger than 1 in absolute value here, the series diverges. It just blows up to infinity if x is bigger than 1, and if x is negative but less than negative 1, it just like, it would be like 1 minus 2 plus 4 minus 8 plus 16. It would bounce up and down, oscillating really wildly. So in both cases, it diverges. So x to the k diverges when the absolute value of x is bigger than 1. We already showed that. And these two situations are both illustrative of a common feature of these power series. There's some certain radius where within that distance the series converges, right? So as long as x is within 1 away from the origin, it converges. But if x is farther away from the origin than that distance, it diverges. So I'm going to give you this term, and then I'm going to define it. So since the series converges when x is less than 1 and diverges when x in absolute value is greater than 1, we would say r equals 1 is the, and here's the new word, radius of convergence. So I sort of kind of tried to define this word with an example, but let me just give you the definition, which itself comes packaged in a theorem. And the theorem is every power series has a radius of convergence. So every power series, I'll do it in general. So centered at C, which as we just saw is something ak x minus c to the k. has a radius of convergence r. That is, and this is the definition this is the definition of radius of convergence. The series diverges when the distance of x to the center is greater than r, and converges when it's less than r. So again, you could see like this series right here, if this was the number line and this is 1 and this is -1, the radius of convergence was all the numbers within that distance r from 0, right? And the next question you should be asking is, okay, so it diverges outside the radius. It converges inside a distance less than the radius from the center. How about on the endpoints? And that, it's not clear. The theorem that I'm giving you doesn't say. So you have to examine the endpoints on a case-by-case basis. The endpoints, they can both diverge, both converge, one diverge and one converge. Like anything can happen at the endpoints. So, well, let's just check what happened with the endpoints here. So, for example, with x to the k, let's check the endpoints. What were the endpoints? Someone tell me. For this one? What were you going to say?
-1 and 1.
Good, yes. So the endpoints plus and minus 1. Okay, so at x equals, let's say, +1. So if x is +1, then the sum of x to the k is just the sum of 1 to the k, which is just the sum of 1, which is 1 plus 1 plus 1 plus 1, which is what? Infinity. All right, this one, just blows up to infinity. So the sum diverges at the right endpoint. Let's check the other endpoint as well. So at x equals -1, x to the k is -1 to the k. So that's 1 minus 1 plus 1 minus 1 plus 1 minus 1. I'm curious, you guys know whether this one converges. Think about this for 10 seconds, and then I want you to take a closed eye, then I'm going to take a closed eye poll. Does this converge or not? Don't say it, just think. Okay, so people don't get embarrassed. Close your eyes and raise your hand if it converges. With your eyes still closed, lower your hands and With your eyes still closed, raise it if it diverges. Okay, thank you. You can all put your hands down and open your eyes. So to examine whether this one converges or diverges, let's look at the partial sums. So, like the first partial, the zeroth partial sum is 1. The first partial sum is 1 minus 1, which is 0. The second one is 1 minus 1 plus 1, which is back to 1. The third one is 1 minus 1 plus 1 minus 1, which is back to 0. Did I do that right? Yeah, the fourth one, we 1 minus 1 plus 1 minus 1 plus 1, which is 1. So the partial sums, in fact, here, so I can even say, so the nth partial sum, it looks like it's 0 when n is odd and 1 when n is even. Okay, so does that sequence, does the sequence 1, 0, 1, 0, 1, 0, does this sequence converge? Does it settle down at one particular number, or at least arbitrarily close to it? No. This sequence oscillates. It does not converge. So the sequence of partial sums does not converge. We say it oscillates. But anyway, the point is, because the partial sums don't converge, because the sequence of partial sums don't converge, the infinite series does not converge. Or, in other words, it diverges. Okay. Let's keep doing some more examples of this. I guess let me point out one thing before I forget to say it about the radius of convergence. It can be 0. It's possible that you could have a series that okay, look. These power series, they always converge at least one point, which is the center of it. Because notice if you plug in x equal to c, then all the terms are 0. So it always at least converges at one point. Right, if I called this f of x, right, if I plug in the center, all the terms except for the k equals 0 term vanish. So it always converges at least one point. If this is the only place it converges, that would correspond to a radius of convergence of 0. On the other hand, what if it converges everywhere? If the series, if this series converges, if this one converges for all x, what would the radius of convergence be? Infinity, yeah. It converges. So yeah, that's having an infinite radius of convergence. So you can imagine, like, if your coefficients are shrinking really, really fast, those are cases when you'll have an infinite radius of convergence. In the example that I just did, where it was the geometric series, we saw that the radius of convergence was 1, and we also saw that it diverged at both endpoints. At x equals plus or minus 1. So thus, we would say that the interval from -1 to 1 is the interval of convergence. Right? These are the points where it converges. So you're going to be asked to find intervals of convergence. It's what I erased that I was trying to draw in blue up here, from -1 to 1, all the points where it converges. So, i.e., the set of points, which, as we now know, is an interval where it converges. Okay, so all these definitions, let's practice some of this stuff. So let's find where, how about x to the n over 5 to the n converges. Okay, so this is a typical question you're going to have on your homework. We've got this series. I'm asking where it converges. But we have tests for this sort of thing. Who's got a favorite test? Yeah, Aiden?
Specifically for the example, it's not my favorite, but the root test.
Yeah, root test is like my least favorite, right? Or mine, well, yeah, it's kind of an annoying one. The ratio test, I like the ratio test, actually. So I think, in fact, both of those would work on this one, actually. Yeah, you could use either one. Okay, he said root test. Let's do the root test. Okay, so usually, like, you guys will do the ratio test, but because Aiden wanted to do the root test, we shall do the root test. Okay, so the root test is we look at the nth root of the term of the series. So it's the nth root of the absolute value of x to the n over 5 to the n. And let's see, this is the nth root of, I can pull the absolute value inside the nth power. Okay. You guys all right with that? How about pull the nth power outside the x over 5? Or absolute value of x over 5. Yeah? And now, you guys can see, I think, why Aiden was inclined to do this test. We get exact cancellation on the powers there, and we just get absolute value x over 5. Okay, good. And now you have to remember what the root test, the conclusion was, it needed the limit of this to be less than 1. So we need the limit as n goes to infinity of the nth root of x to the n over 5 to the n to be less than 1 in order for it to converge. But I just calculated this. You might notice we're not even going to have there's not even an n anymore. The n canceled out, right? This is the limit as n goes to infinity, but the n's are gone, so of just x over 5. So if there's not an n, it's just the same, right? There's no n to even take a limit of. So this is just absolute value of x over 5. Okay. So we need the absolute value of x over 5 less than 1 for the series to converge. I.e., we need absolute value of x less than 5. So what's my radius of convergence? How about someone from over here who hasn't responded yet? Who wants to volunteer? What does it look like the radius of convergence is? Oh, I know Aiden knows. How about? It's 5. Good. Right, because another result of the root test was that if this number is bigger than 1, it diverges. So if absolute value of x is bigger than 5, this thing would diverge. And it kind of makes sense. Like, look at this. This is the same as the sum of x over 5 to the n. Well, if you just like kind of look at this and think about it, oh yeah, it makes sense we need x less than 5. So that when we raise it to a power, the numbers are getting smaller. And if x is bigger than 5, then we're actually getting numbers that are blowing up and getting bigger. So this is kind of like just the answer you would expect. And you'll find that's the case. On a lot of these problems, you kind of get like the no-duh answer. And it also helps once you start remembering which functions beat which ones. Like that factorials beat exponentials and so forth. We'll get to all of that, but now that we found the radius of convergence, is the question done? No. What's still left to be done? How about someone on this side of the classroom? What's still left to be done? The endpoints, good, yeah. So next step, you can kind of say, first step was to do the root test. Second step is to check the endpoints. So the endpoints are plus or minus 5. Okay, yeah, I want you guys to check these endpoints. So check x equals plus 5 and check x equals minus 5. I'm going to give you a minute and then take a poll and see if you guys get whether it converges or not at those endpoints. So, yeah, we're going to have two choices. It either converge or diverge. And here, it either converge or diverge. Okay. Now, again, so everyone close your eyes so no one's embarrassed. We're going to start with positive 5. With your eyes closed, raise your hand if you think it converged. Put your hands down. With your eyes closed, raise your hand if you think it diverged. Okay. I think we got about 1/3 of the class saying converge and 2/3 saying diverge. How about at -5? Close your eyes. This is at -5. Raise your hand if you think it converged. Okay, put your hands down. With your eyes closed, raise your hands if you think it diverged. Okay, about the same split. You can put your hands down and close your eyes. Or open your eyes, I mean. Okay, so let's check what happens. So at x equal 5, it's the sum of x to the k over 5 to the k is the sum of, well, x over 5 to the k, which is the sum, if x is 5, it's just 1 to the k. It's 1 plus 1 plus 1 plus so and so forth, which we already saw. So this is actually just like the example I already did, actually. So it diverges. And similarly as before, at x equals -5, it's the sum of -5 over 5 to the k, which is -1 to the k, which is 1 minus 1 plus 1 minus 1 plus so forth, which diverges. Okay, so it diverges at both endpoints, but we already know it converges inside x, a distance 5 from 0. Thus, the interval of convergence is the interval from -5 to 5, right? Or it's the same as the set of x such that -5 is less than x is less than 5. Okay. Man, I guess I'm not going to have time to, I'm going to run out of time if I try and alter this example. But next time, I'm going to show you what would happen if I put an x to the k over k times 5 to the k. And we'll see that in this case, it will converge at one endpoint, but diverge at the other. So, okay. I'll see you guys on Friday.